Hello once again, class, and welcome to another mock lecture. Today we're just going to be talking about some basics on sampling. We're going to start off with the definition of a population. The population of a study group is the group that the collected data is intended to describe. So let's say that we want to conduct a survey on a population of shapes. What I want to know is what's the average number of distinct pen strokes each shape has in this population. So the circle can be 1 pen stroke, the cross can be 2 pen strokes, the triangle can be 3 pen strokes, and the square is 4 distinct pen strokes. If we survey the entire population, then what we're conducting is actually called a census. It's a survey of the entire population. So if we were to count every single one of these things and then add up all of the distinct pen strokes that there are for all of them, and then divide that by the total number of shapes that there are, that would be the census. We'd be using that whole population to find this average pen stroke per shape. And that value is called a parameter. A parameter is a value, like an average or a percentage, that's calculated using the entire population. So you might have noticed these numbers down here represent how many of each shape that there are. There's 24 squares, there's 24 circles, there's 16 triangles, and there's 32 crosses. So if I were to go ahead and find the average number of sides, a number of pen strokes, I guess I should say, with this calculation, given that there's 96 shapes total, we get 2.42. Okay, that's our parameter. So any shape in here has, on average, 2.42 pen strokes. Now, maybe the sample's too large to get a census. Maybe there's just too many things to count up. And so what you might want to do is survey just a sample of the population. A sample is a smaller subset of an entire population, ideally one that is fairly representative of a whole population. And when we use the phrase fairly representative, what we mean is that it's similar to the full population in every way possible. So here is a sample of the population. And, I knew from before that there were more crosses than there were squares and circles, and the least amount of shapes there was triangles. So I selected a sample that was, somewhat reflective of those qualities. Now, when you find your average or your percentage or your value, that would normally be considered a parameter when you're conducting a census and calculating that thing. When you're doing that for a sample, that's called a statistic. So it's a value, like an average or percentage, that's calculated using the data from a sample. And we use this statistic to estimate the parameter. That's why you want it to be similar to the population. So if I calculate the statistic here based on this sample, there's only 4 squares, there's 4 circles, there's 2 triangles, and there's 6 crosses. And if I figure out the number of pen strokes pertaining to each of those things and divide by 16, because in this sample there's 16 shapes, I get 2.375. And so what I would say is okay, well, then 2.375 is going to be about what the average number of pen strokes for any shape in the entire population. We use this estimate for average shape pen strokes to say something about the whole population. So instead of having to survey the whole population, conduct a census, we're just, finding a sample and calculating our average based on that sample. But that's called a statistic, and it's used to estimate a parameter of a population. The problem is that this can vary wildly depending on the sample that you get. Like, for example, maybe in this case, I didn't select any circles, right? I got 8 squares, 5 triangles, and 4 crosses. My statistic here is 3.44. So we'd be using this statistic to estimate the parameter for the whole population. What we'd be saying based on this study is, hey, look, the average shape in our population has about 3.44 pen strokes. But obviously that's pretty far off, right? It was 2.42 or whatever it was from before. And so this isn't a great representation of the population. Whenever this happens, that's called a bias, right? If the sample that you're using isn't representative of the population, that's what a bias is called. So I want you to pause the video here, and I have 5 different bullets here. What I want you to decide is whether or not the bullet point that's listed is a parameter or a statistic. All right, well, let's go through them here. I'm just going to put all the answers on, and we'll talk about why each one is what I decided that they were. I said the first one's a statistic, because unless they're surveying every single kid that's aged 6 to 8 in the entire world, then it's a statistic. If they were able to do that, then okay, then it'd be a parameter. The second one I also said was a statistic. 3 out of every 5 households in America own a pet. Again, unless they somehow surveyed every single household in America to come up with this and then reduced it to 3 out of 5, it's a statistic. The third and fourth ones I said were parameters, right? The third one says a high school teacher reports the average on the final exam being 72%. Well, the high school teacher should know what the actual average is. All of her students, were able to take the exam, and so that was something that was calculated based on her whole class being the population in that case, so that one's for sure a parameter. The fourth one says 1/4 of the people in my household like spicy food. That's a parameter. There's only 4 people in my household. I'm the only one that likes spicy food. So I surveyed the entire population whose opinion I wanted in my study. Right? That's the census of my house. The last one I said was a statistic because it says the average female height in the USA is 5 foot 4 inches. And again, unless every single female in the entire United States was measured, then this is a statistic. Okay, so to get some of this stuff in writing, a representative sample is a sample that is similar to the population in all characteristics. Sampling bias is when the resulting sample is not a representative of the population. And then finally, sampling variability, which is the unavoidable natural variation of the samples. Pretty much no matter what sampling method that you use is going to have some sampling variability in it. For the most part, sampling variability isn't that big of a deal, but things like this can happen, right? It is possible to just randomly select all circles, for example. So let's talk about the kinds of sampling methods that there are. First, there's random sample, and this is when each member of the population has an equal probability of being chosen. Something like this would be a random sample. I just randomly kind of threw darts basically at my screen to select this particular sample of 16. A real-world example of this might be in a class of 100 students, you want to put names on a slip of paper and then select 20 of them at random, right? Shuffle them all up, select 20 of the papers in a hat or something like that. The next type of sampling method is arguably the best kind. It's a stratified sample, which is when a population is divided into distinct number of subgroups that are called strata. Random samples are then taken from each strata with sample sizes proportional to the size of the subgroup in that population. So again, let's look at these numbers. We know there's 96 shapes total. There's 24 squares, 24 circles, 16 triangles, and 32 crosses. If I convert that, if I find what proportion of the entire sample each distinct shape is, I come up with these. 1/4 of the shapes are squares, 1/4 of them are circles, 1/6 of them are triangles, and 1/3 of them are crosses. So we want our sample to have this same kind of construction. Like when we make the sample, we want 1/4 of the sample to be squares, 1/4 to be circles, 1/6 to be triangles, and 1/3 to be crosses. So we can be smart about the size of the sample that we should choose. 12 is actually the best one because it's divisible by all of those denominators there. You can break it into fourths, you can break it into sixths, you could break it into thirds. You could also do like 24 or any multiple of 12 would be fine as well, but 12 is I think the simplest sample to choose for this population. So let's say we choose this. There's 3 squares, 3 circles, 2 triangles, and 4 crosses. That sample, each particular shape, is the same proportion within the sample as it is within the population. So when we find our average number of pen strokes, we're actually going to get the exact same thing. So we would say that this sample is a great representative sample. For a real-world example of this, let's say that in a middle school with 100 fifth graders, 200 sixth graders, and 200 seventh graders, we want a stratified sample of 40 students to ask something, right? Some kind of question. So we want our sample to be 40 students big. So we need to figure out, well, what proportion of the population is fifth graders? What proportion of the population are sixth and seventh graders? To do this, for fifth graders, since there's 100 out of the 500 students are fifth graders, we can reduce that ratio to be 0.2, which is equivalent to 20% of the population. So 20% of the school population is fifth graders, which means that we want 20% of our sample to also be fifth graders. And if we want 40 of them, just multiply 40 by 0.2, so we get 8. So 8 students in our sample should be fifth graders. As for sixth and seventh, both of them have a population of 200 within the total population, which is 40% of the total population. So we want to also have our sample. We want 40% of our sample to be sixth graders and also 40% of our sample to be seventh graders. So again, we multiply 0.4 by 40. So we get that we should have 16 seventh graders and 16 sixth graders. So the breakdown will look like this. We want to select at random 8 fifth graders, 16 sixth graders, and 16 seventh graders, and that'll give us a stratified sample of 40, which will be a good representative sample for our population. Next, there's quota sampling, which is a variation on stratified sampling, wherein samples are collected in each subgroup until there's some desired quota that's met. So the real-world example that I put here is, let's say that an app developer wants to survey 250 people between the ages 18 and 30, and then 100 other people. So they want the majority of their sample to be people that are aged between 18 and 30. So this might have happened to you before. Someone calls you and says, "Hello, we're conducting a survey about studying other languages on your phone. Are you between the ages of 18 and 30? And you say, "Yeah, I'm 25. And they say, "Okay, well, we've met our quota for that age range. Thank you for your time." And then they'll hang up on you because they've already, they've met their quota for that. They're looking for people outside of that range. All right, next there's cluster sampling, which is when a population is again divided into subgroups, this time where they're called clusters, and a set of subgroups is selected to be in the sample. Different than stratified, because in stratified you're randomly selecting within the subgroups that you set up. But with cluster sampling, what you're doing is you're making clusters, you're making subgroups, but then you're surveying every single person that's within the subgroups that you randomly chose. A real-world example of this would be like to survey students at a university, you randomly select 4 classes and give the survey to all the students in those 4 classes. Then there's systematic sampling, which is sampling every nth member of the population to be in the sample. So here I tried to count out every 5th shape, but this would construct the sample. Some kind of systematic way to determine who's in your sample. A real-world example of this might be a survey given to every 10th customer entering a storefront. And then there's 2 not-so-great methods of sampling. The first is convenience sampling, which is when you choose a sample based on whoever's convenient. So maybe you just survey immediate family members and friends who all might have the same kind of opinions that you do. And then there's voluntary response, which is when you allow the sample to volunteer. And oftentimes people who are willing to volunteer for stuff like that have a certain mindset. And so you're introducing some kind of bias into the sample that you're collecting. So recall that sampling bias is when a sample is not representative of the population itself. There's many different factors that we can point to that would contribute to a biased sample. And so here are the types of biases that can exist. The first is, as I just mentioned, voluntary response bias. It's the type of bias that often occurs when the sample is a bunch of volunteers. So think about things like Yelp or Rate My Professor. Typically, students that write reviews on these websites are either have a very positive experience and they want to write about it, or they have a very negative experience and they want to write about it. There's not a whole lot of the people that are kind of in between, right, in their opinions. Self-interest study can be another type of bias, and that's a bias that can occur when researchers have an interest in that particular outcome. So imagine if Kellogg's released a study that read something like, "Study shows eating cereal for breakfast can increase energy throughout the day." But it's by Kellogg's, and it's about how eating cereal is positive, and maybe this study should just be about eating any kind of breakfast in general, right? Increases energy throughout the day. Or maybe you've heard like the 10 of 10 dentists choose Crest or some brand, but then the study was sponsored by Crest and the dentists that were surveyed are already using the product, right? That's a self-interest study, kind of to self-promote. Response bias just in general is when the responder gives inaccurate responses for any particular reason. So like, for example, a survey about how many hours people look at their phones. Like people might not want to actually disclose how many hours that is. And I've broken this up into kind of 2 subcategories. One is maybe they have some perceived lack of anonymity. So when the responder fears giving an honest answer might negatively affect them. Or some kind of loaded question, like when the question wording influences their response. So an example of that might be something like, "Do you support funding green energy to save the planet?" But that's a loaded question, right? Because whether or not you do want to support funding green energy, saying that it's to save the planet might, make someone who doesn't support funding green energy second guess themselves because they want to save the planet. So a better question would be, do you support funding green energy? And then just leave this part out. Then there's non-response bias, which is when people refuse to participate in a study that could potentially influence the validity of that outcome. Okay, so those are all the potential biases, right? Anytime you select a sample, you have to think about, am I introducing bias, or am I somehow minimizing the effects of potential bias in my way of sampling, my method of sampling? All right, now I wanted to end this video talking about categorical versus quantitative data. So categorical data is when pieces of information that allow us to classify the objects under the investigation into various categories. So for example, stuff like survey about eye color or favorite sport or yes or no polls. There's no numerical piece to this. It's each distinct category. So in the case of eye color, it's like blue, brown, gray, green, so on and so forth. Quantitative data is when pieces of information that are numerical in nature is the data that's being collected, and with which we can perform meaningful arithmetic operations on. So an example of this would be like average age, right? Or average height, or average number of pets, or something like that. And all of those I'm using average, but it doesn't necessarily have to be an average that you're after. There are some tricky situations, though, for whether or not you might determine if the data you're collecting is categorical or quantitative. For example, what if you're surveying people to figure out what the last digit of their phone number is? Well, if you look at the quantitative data definition, a phone digit is numerical in nature, so it satisfies this first part of quantitative data. But can we really perform meaningful arithmetic operations on the last digit of a phone number? I would say no, not really. Like finding an average last digit of a phone number, you may end up with a decimal, and that doesn't make any sense in the context of a phone number. So as it turns out, something like the last digit of a phone number, that is actually categorical. So sometimes you really have to ask yourself, is this truly quantitative data? Like a social security number, right? For example, that's not really quantitative data. That's categorical because it's an identification, not necessarily something that you're going to use to calculate with. All right, so this video was a little bit longer than normal because I wanted to cover kind of all the basics of surveying, sampling, and biases, and methods of sampling, and categorical versus quantitative stuff. But hopefully you guys learned something. If you have any questions, drop a comment below or shoot me an email. Thanks a ton for watching, and I'll see you in the next one.